Welcome to the next edition of Network Security. In the previous video, we saw a really cool attack that allowed an off-path attacker to infer communication between two communicating parties, even though he had no visibility of the packets that they sent. And not just that, but even determine the source port that was being used, the sequence number, and the acknowledgement number. In other words, all the information that the attacker would need to terminate that connection or even to inject data into that connection. So a proper off-path TCP hijacking exploit. And then this was fixed in Linux version 4.7, and that was the end of it, or so we thought. But it turns out that this is not. And this is another important lesson in security. Very often, once people are aware of a principle that they can use for an attack, they will, even after a fix, will look for new ways to still abuse a similar principle, or the same principle, but in a slightly different way. And this is what's happened in this attack that that came out in 2020 and is published at the CCS conference in the fall. And it's called Off-Path TCP Exploits of the Mixed IP-ID Assignments. And what we're going to do now is look at this attack and see how it relates to the previous attack, and also see how it works in general. So the new attack, as we shall see, doesn't use the global rate limit anymore, because the global challenge act limit, which was the source of the problem in the previous attack. We no longer have that, but instead what the attackers do is use the IP identifier, IP-ID, as the sort of shared counter. Okay, the IP identifier is a number that is given to every IP datagram that is sent out, right? And it's used, for instance, in case of fragmentation. If you have a packet that's fragmented in the network, it needs to be put together at the destination again. And the way the destination does that is by looking for all the fragments that have the same IP identifier. Okay, so we have to pick some value for this IP identifier. Every packet, every datagram has to have a unique IP ID. And this has to be done securely. Okay, so this is what we're going to be abusing, because it's not always secure. So our attack still uses the same challenge act. So this was a nice discovery, and the new attack can use that also, but it uses them in a slightly different way. Okay, so let's look at this IP identifier and worry a little bit about how the TCP IP stack picks the right, counter, the right identifier for this field in the IP datagram. Okay, so for Linux versions later than 4.18, there are two ways to select a counter to use for the IP ID field. And the first way is to do this per socket. You have your unique counter for your socket, and it's yours alone. And this is a secure way. Okay. But besides this secure way, there's also a slightly less secure way, which is based on, you pick a counter from 2048 counters that are picked on the basis of a hash. So you hash based on some information that we'll look at in a minute, and then you pick one of those counters, and that's the counter that you're going to be using for. And that means that you may not be the only sender the only information transfer that uses that same counter. Okay. So let's see how it works in practice. The packet that is being generated, so the packet that that needs to be sent, is evaluated according to the following algorithm. First, we see if it's a reset packet, and if so, we give it IP ID 0. And the reason for that is yet another side channel. Let's not get into that. That's a different attack. Okay. If it's not a reset packet, it will look at the DF field, right? The DF field in your IP datagram indicates whether or not your packet can be fragmented. And if this has a value 1, we will actually use the secure per socket counter, okay, unless your packet happens to be a SYNAC, in which case we also set it to IPID 0. Okay, so if the don't fragment field is 1, which is normally the case for TCP, we actually use this secure counter, right? So the counter that is unique for this particular socket. Okay. Now, if this is not the case, if the DF field is not equal to 1, we will use a slightly less secure counter, which is based on this hash bucket, right? So your hash, and then you actually obtain a counter from a bucket, which is shared. So there's 2048 of them, but in the end, it could be shared. And normally, the IPID will be picked per socket. So this is a normal mode of operation, and this hash-based counter is unusual, okay? Because normally the DF field, the don't fragment field, is equal to true. So what the attacker will do, and as we shall see, is it will first degrade the counter to use one of those less secure counters. So it tries to ensure that we don't pick this secure counter that is per socket, but we use one of these hash-based counters. Okay, and then we use that as the basis of our side channel. So let's see how we do that. And the attack consists of 3 main steps. First, we detect the victim client. So we're interested in maybe hijacking some connection between a client and a server. And what we're going to do is we're going to force the server's IP ID assignment from this secure socket per socket policy to this hash-based policy. Okay? And then through hash collisions, we can determine hash collision. We can detect that the victim uses the same IP ID counter as the attacker. And then we have a shared counter, which is great. We have to be a little bit lucky there, or we have to have quite a few IP addresses that we control. But in principle, it's a viable way of doing things, as we shall see. The next step, we're going to detect the TCP connections and the source ports, right? And we do that again by sending spoofed packets, right? So we impersonate, in this particular case, the client, and we send some spoofed SYNACs, and then look at what happens to the IPID field that we share, right? So it's a shared counter with this victim, right? So that's what we did in step 1. And as a last step, a final step, we're going to infer the sequence number and the acknowledgement number. And then we do this again by sending spoof packets, in this particular case, reset packets and acknowledgement packets, which will trigger these challenge acts. And again, then we look at changes in the shared IP ID counter to determine the correctness of our guesses for the sequence number and the acknowledgement number. Now, the principles are similar, right? So we look at the number of challenge, we look at the challenge acts to determine whether or not the guesses that we made are correct. But we approach it, as we shall see, a little bit differently. So let's start with step 1, right, where we want to downgrade the server's IP ID assignment from the secure per socket policy to the hash-based policy. Okay. And to do that, we're going to look at this DF field, the don't fragment field. We already saw that if the don't fragment field is set, we go to per socket ID counters, and if it's not set, so if it's 0, we'll use this less secure hash-based counter, which uses 2048 elements. Now, the interesting thing is that we can actually clear the DF flag by as an off-path attacker even, and then downgrade this IPID counter assignment by sending an ICMP message. So if we pretend to be the router, if the attacker pretends to be the router, and it sends a forged ICMP fragmentation needed message. So the server will receive this message and say, oh wow, it seems like the some router on the path requires fragmentation. Okay? Okay, some router between the server and the client has a smaller next hop MTU, maximum transfer unit. Okay? Even though it says that the packet should not be fragmented. Okay. Now that is a nice trick, but does it actually work? Well, it's not so easy, unfortunately, for the attacker, because you need to get that ICMP packet to be accepted, and for that you actually need some content that makes sense. So even though the server doesn't validate the source of the ICMP message, it must have the right sort of data. So the data embedded in the forged ICMP packet must evade two checks. Okay, so according to RFC 792, the error message should contain at least 28 bytes of the offending packet. Okay? 28 bytes of the offending packet you must provide correctly. Okay? And in the newer RFC 1812, it even says that the ICMP error message should embed as much of the offending packet as possible, okay, but less than 576 octets. How do we provide the right sort of content so as to bypass these checks? We don't know this information. So what to do? Well, what we do is we're going to embed some ICMP reply data. So ICMP reply data into this forwards ICMP message. Okay, which is kind of weird because we're supplying some other data. But the good thing is that if your Linux server receives an echo reply embedded in a message, an error message that says fragmentation needed, it doesn't know. It doesn't know whether this is actually a reply to a request that it sent. It didn't ever send this request, but it doesn't know this. So it's going to assume that this is indeed correct. And thus it responds to this forged ICMP message. And here's the interesting thing. It will now clear the DF flag of all the subsequent packets that are sent to this client, okay, whose IP address is in this embedded echo reply. Okay, so what we're sending is an IP header, an ICMP header, and then an embedded echo reply that is easy to provide. Okay, and then we actually have downgraded the server from using the per socket counter to the hash-based counter. Okay, so now we have this hash-based IP ID because the server will assign these IP IDs by using one of those 2048 hash-based counters. That's still a large number of counters, right? So if we want to use this as a side channel, we have to make sure that we have the same hash-based counter as the victim uses, right? So because this is what we want to see what's happening to the counter that is also used for the victim. It has to be shared between the victim connection and your connection. Okay, so that's a challenge. How do we do that? Well, let's look at how this how the hash bucket is selected. So how do we pick our counter? In other words, it's used by means of a hash over the source IP, destination IP, protocol number, right? So if it's TCP, it will be 6, and some random key, some random value. Now, all of the numbers we know, but we don't know, of course, the random key. But if we manage to get these TCP packets sent that is sent to the victim client have the same hash as the packets that we send to the attacker, right, then we will be using the same IP ID counter, so the same bucket. And that's what we want. So we want this collision. We want this collision in the hash so that we have the same IP ID counter. And what we have, so there's a lot of stuff that we don't have, right? So we know the destination IP, we know the source IP, we know of the victim, we know the protocol number, we don't know the random value, right? Of course, but that's going to be the same in both cases because that's a boot key that is used at the server side. And the only thing that is variable is the IP address, the IP address of the victim and the IP of the client and the IP address of the attacker. Okay. So what we want to do is we want to see if we do have a collision, right? So, and if we have a collision with an interesting IP address. So maybe there's a couple of IP addresses that we want to. And we do that as follows. So there's two scenarios. We're going to use the fact that the IP identifier changes and look at by how much it changes to determine whether or not we actually share the hash-based counter. So let's first consider the case where there is no collision, right? So we don't use the same hash-based counter as the client that as is used for the client. Okay. So this is what we do. Here's the client, here's the victim server, and here's the attacker. The attacker first sends this ICMP message saying that we need fragmentation, and that means that the DF flag will now be cleared for all communications with that client, with the victim client. Okay. Next thing we do is we send a request where the source IP is the attacker, right, and the server a legitimate request. And the server will reply, and the reply we don't care about, except that we want to know what the IP identifier is. In other words, we measure the IP identifier. Okay. Now, the next thing we do is we try the same thing, but now we spoof with the IP address of the client. Okay. We try to set up a connection, a SYN connection, a SYN packet to start this TCP handshake. The server will, because it's a spoof packet, reply to the client. Now, if the client and the attacker do not share the same hash bucket, right, it will pick a value that is not related to our value. In this case, it picks the IP ID 4444. Okay, and that's unfortunate because the attacker hoped that it was somewhat related to this IP ID. But he can easily measure that this is the case by sending another request to the server, and again measuring what happened to the IP ID. Okay. And if the IP ID is only incremented by 1, it means that this value was not generated with that same counter. Okay. So in that case, we know that we were unsuccessful. We don't have a collision. Okay, not with this client. Maybe we should try a different client. What if there is a collision? Well, in that case, we go through the same procedure, right? So the attacker sends this ICMP message, the DF flag gets cleared, we send a request, we measure the IP ID, and then we send another spoofed message pretending to be the client, a SYN, and then the server replies to the victim client with a datagram that contains an IP ID that is the value that the attacker measured plus 1, right? And that means that if the attacker subsequently measures this value again by sending a request and looking at the IP ID, it will be the old IP ID plus 2. And now we know that we actually are using the same hash bucket. Okay, so that's great. So does this give you exactly the IP address of the client? No, just know that it's in the same bucket. It hashes to the same bucket. So it's actually a little bit more complicated than this because normally the hash-based IP ID counter does not increase linearly. So the increment is some random value in a uniform distribution between 1 and the number of system ticks since the last packet transmission that used the same counter. Complicated. So how do we deal with that? So we have to somehow make sure that, or try to make sure that it does send these counters in a way that they increase linearly. Okay. And the way to do that is by restricting the number of system ticks that are related to this particular IP ID counter. For instance, if we send 3 packets in less than 10 milliseconds, the random value that is added to this IP ID counter will never be greater than 1. Okay? So we just have to be quick about it. And by sending ICMP request packets to the server in parallel, the attacker is able to restrict the increment of the system ticks. So in practice, if the round trip time from the attacker is 200 milliseconds, we need less than 300 packets to force this linear increase. Okay? So that's definitely doable. So let's have a look at a few more details and consider the probability of the collision. So if you have a number of IP addresses, say K addresses, that you can control, the probability of an actual collision between the attacker and a target client. So if you have a target client, is 1 minus p to the power k. Okay, where p equals 1 over 2048. Okay, so it goes up reasonably quickly, but even with a single IP address, the attacker can find clients that have a collision, right? So, and I'm not going to discuss this in detail. See the paper. You can find lots of potential victims, 2 to the power 21 potential victims that would hash to the same bucket. Okay? But so the point is, if you are a powerful attacker, you may have more IP addresses, and if you have say greater than 2048 IP addresses, you can probably attack any IP address, right? So you need a few thousand IP addresses to attack any target IP address with a probability of 63%. Now, this is definitely not infeasible for even mundane attackers. Okay, great. So, for instance, you could just rent a botnet with a bunch of IP addresses, and you'll quickly get that. Now, you're probably thinking, this sounds too good to be true, right? Because surely there are other clients that are active, right? So it's not just you, and you have to be able to measure this very precisely. Otherwise, you'll be measuring increments of 2, even though there was no hash collision. How can you make this? How can you make this work in practice? Well, in reality, so this is, I think, on the next slide. So what if other clients are active? Well, it turns out that this is not so much of a problem, right? Because the other clients are typically using this per socket IP ID counter. It's not common to use this less secure hash-based counter, and this is something that we can now use to our advantage. So the next step is to detect connections, right? So we want to find the source port, for instance, the source port and the source IP address, the exact IP address, not just something that maps onto your hash counter. In theory, this is not very complicated. So what you can do is simply send a continuous stream of ICMP echo requests and observe the IP ID values, right? And also send a SYNAC, one SYNAC packet with a guess for the source IP address and the source port number. Okay, assuming that you don't know the source IP address. If the source port is incorrect, a reset packet will be sent to the real client with IP ID equals 0, right? So there's no change to the counter. Okay. If the source port is correct, a challenge ACK will be sent, and that means a jump in the counter. So this is how we can observe these these situations. The question is this practical? So the port range is reasonably large. It should be, in the theoretical case, it should be 2 to the power 16, but by default, the range of source ports on Linux is much smaller than that. So it's between 32,768 and 61,000, and on Windows, it's even smaller than that. Okay, and here, just like in what we saw earlier, the attacker can use binary search again. So in practice, the answer is yes, this is practical. You can find a connection in about 40 seconds is what the paper reports. Okay, so you basically can do this in a batch, and then half the batch, and then half the batch again, and so on. Okay, so we can detect connections. So our final main step is now to find the sequence number and the acknowledgement number. We have all the other details, and this is a complicated step, right? So we now divide up this big step into small steps, 4 sub-steps. And the first one tries to find acceptable sequence numbers, so the numbers that are in the receiver's window. And then we try to locate the challenge ACK window, so this red part here, so we try to find that, right? Then we try to detect the lower boundary of the sender's receive window, so the exact sequence number that is the lower bound of the sender's, the server's receive window. Server's receive window, I should mention that. I think I said sender's receive window. And we do that based on the acceptable sequence number and the challenge ACK window that we found in the previous steps. And finally, we look for acceptable ACK numbers through probing the boundary of challenge ACK window and inferring the boundary of the server's sender's window. Okay, so that's the plan. Now let's do this. And we use the procedure that we already discussed in the discussion of the previous paper. So whenever a packet is received, it will be subject to some checks, right? So first of all, it will check the sequence number. So the sequence number has to be within this window. So receiver next and receiver next plus the size of the window. Okay, and receiver next and receiver window are the sequence number of the next octet, so the next byte that the receiver expects, and the size of the window. Okay, so and if you pass that, it actually starts looking at your acknowledgement number. So that has to be in the acceptable acknowledgement window. The acceptable acknowledgement window. And that is true if the acknowledgement number is somewhere between the send next, right? So the next thing that I want to send, and send next, yes, and the send unacknowledged, the first unacknowledged byte minus the sender's maximum window size, right? So the maximum window that we've ever observed. Okay, send max window is the maximum window size that the receiver has ever seen from this peer. Okay. Then it's in the acceptable ACK window. Okay. If not, right? So if it's in the window before that, so in the sec.ack is in the unacknowledged, so the first unacknowledged byte minus 2 to the power 31 minus 1, and less than the sender's first unacknowledged byte plus the sender's maximum window size, then it's in this ACK window. Okay. Sorry, minus the maximum window size, of course. Okay, then it's in the challenge ACK window. Okay. So what we can do is we can infer these acceptable sequence numbers by continuously sending ICMP request packets to the server and again monitoring the IP identifiers that we get in the replies, and then send a spoofed reset packet. So we send a spoofed reset packet where we guess a sequence number. And again, we use this side channel, similar to the side channel that we used in the previous attack, but now we're looking again at the IP identifiers. Okay, if the IP identifier does not experience a counter increase, it means that the packet was discarded, and so it wasn't in the server window. Otherwise, however, a challenge ACK must have been sent, and that challenge ACK uses that same IPID counter, so it must have led to an increase of the counter. And now we can determine that the sequence number is in the acceptable range. Okay. So in the case it's in the acceptable range, we should see a jump in the IP identifier. It shouldn't just increase by 1 by 1 by 1 by 1 by 1. It should all of a sudden see an increase by 2. Okay. And again, there are optimizations, but we don't talk about those. Next thing to do is to locate a challenge ACK window. Okay, so that was the second sub-step. So what we do is whenever, in general, right, so when we receive a data packet, there are 3 options. There's an acknowledgement number that is in the challenge ACK window, it's in the acceptable range, or it's invalid, right? So we've seen that in the previous attack already. Okay, only in this case, a challenge ACK will be sent. Okay, and if there's a challenge ACK, again, we can detect this because there will be a jump in the IPID counter value. So the procedure is very similar to what we saw earlier. We again observe and record the shared IPID counter. We can do this by continuously probing for that. And then we send one spoofed ACK packet, some data packet, with a guess for the acknowledgement number, right? And the sequence number that we already guessed to be in the that we already found to be in an acceptable range. Okay, we send that, and then we again look at what happens to the IP identifier. If the ACK was in the challenge ACK window, so in this chunk that we saw in the red chunk that we saw in the picture, then a challenge ACK packet will be issued, and that will make the IP identifier counter jump. So we can measure that again. Now we know the acceptable ranges, but the next step is to find the exact sequence number. So we want to detect what in the figure was indicated by receiver next. So that is the lower bound of the receive window. This is the first byte that the receiver is waiting. And the procedure of that is to forge multiple acknowledgements with a constant acknowledgement number located in a challenge ACK window and a sequence number that is set to a sequence number that was acceptable minus some value I. Okay, so the acceptable sequence number that we found earlier minus some value I. Okay, and we can run this for some time, and we'll see that initially this challenge ACK will be generated at a rate of 1 packet per 500 milliseconds due to the rate limit in the challenge ACK, and that would trigger regular updates to the shared IP ID counter. So this is what happens even though we actually move the sequence number to the left on the picture. Okay. But at some point, the sequence acceptable minus I will reach this lower bound of the service receive window. And once we have that, we actually see that the server starts sending duplicate ACKs without rate limit, and that will also increase this this IPID counter, and that should be detectable. So now we know the exact sequence number. We know the boundary of the receive window on the server side. Next step is to detect the acceptable, at least some acceptable acknowledgement number. So how do we detect the acknowledgement number? Well, we do something similar to what we saw in the previous slide. So what we constantly probe for the IP ID counter using these probes, using probing acts. We start sending forged packets, so forged probing acknowledgements that have the sequence number initially set to sequence acceptable, and the acknowledgement initially set to the acknowledgement challenge that we had earlier, right? So we had this ACK challenge. Right, so the sequence number will be set to the sequence acceptable. So before we started lowering this, and the acknowledgement will be set to ACK of the challenge and then -1. So if we have an initial ACK that is in the challenge ACK window, we start decrementing this until we reach the lower bound of the challenge ACK window. Okay, so we keep doing this, and eventually we'll have depleted this challenge ACK number. And then once we know the base of the challenge ACK number, we can also easily determine the actual sequence number of the first unacknowledged byte, right? So the sender UNA, as we called it, by adding 2 gigabytes to the detected boundary. Okay, so that's what we do. We keep decrementing this until we reach the bound of the challenge ACK window, add 2G, so half of the entire space. The entire space is 2 to the power 32 or 4G. We add 2G to this, and then we get to the SND.UNA, so the first unacknowledged byte, and that should be in the acceptable ACK range. Okay. And when all the data that we sent earlier has been acknowledged, the value should equal the sender's next, so the next thing that the sender needs to send. Okay, so that is how we do this. Yeah. There's an alternative, right? So to finding this, if there's still data to be sent to the client, we can also find it by adding the typical size of the send window to the value of send UNA, so this value of first unacknowledged byte. Okay, great. So now we have that. Let's move on and show how we now have the complete attack. Okay, so what the authors in the paper show is that they can do several attacks, such as connection termination. They show that for different versions of Linux, they're able to reset the connection or terminate the connection within a few hundred seconds. So it's it's practically fast. So it's a practical attack. Okay, and they can do this in many versions of Windows with a very high success rate. So 9 out of 10, 10 out of 10, that is really high, and with very limited bandwidth. So a few kilobytes per second is something that is definitely within the capabilities of even very modest attackers. Okay. Moreover, what they've done is a kind of cool experiment where they inject data into an existing connection, where there's messages that are viewed by a set of group members, and something is added into this connection. So there's a fake ad that is added into the message. Okay, and again you see that the time it takes to pull off the attack and the bandwidth it takes to pull off the attack is all within very reasonable limits. So 54 kilobytes per second and some 120 seconds to do this is quite impressive. So now we have the full attack. So what are the lessons learned? Well, first of all, the problem of doing the mitigation against the Challenge Act seemed to be a very simple problem, right? So there was this um, shared global counter that we just needed to eliminate, and then we'd be done. But it turns out that doing so, it's much more complicated because there may be other sources for this side channel. Okay. The other thing that we've learned is that very often solutions for security problems, right? So proposed fixes have their own security problems, and they may be worse than the original problem. Okay. The other thing that we've learned is that side channels are realistic threats. You can build practical attacks on top of this. So all of these things are interesting. And the final thing that we've learned is that this, decades old problem of TCP hijacking, which, was complicated even back then, right? And it's been made more and more complicated. It's still an issue in 2020. Okay. So that's interesting. So with that out of the way, we're going to move on to other kinds of attacks, such as denial of service attacks in the next video. And we later on will also look at scanning. So if you want to find out which services are running on a particular host, we can use techniques such as port scanning. Now, interestingly, as we shall see, one of those scanning techniques, and this is a forward reference because it's not in the next video, but one of those scanning techniques will actually use something that is a little bit like the previous attack, the attack that I talked about in this video, in the sense that they also use this counting of the IP identifier, so the field in the IP datagram that is the IP identifier. Okay, but that is for a later video.